This video introduces more of the basic rules for proofs in SL, including some rules that require subproofs. Recall that there are 11 basic rules of proof, reiteration, plus an introduction and an elimination rule for each connective. The basic rules are enough to give a proof of every valid argument. So far, we've covered 7 of the basic rules. This video adds conditional and biconditional introduction. Also note that all of the rules of proof are included on a 2-page reference sheet. That appears in the last 2 pages of the textbook. You can download it as a separate PDF. These are a valuable reference. When watching me work through a proof, you'll understand it better if you compare how the application of the rule looks in the proof to the version that appears on the reference sheet. And it's also useful when you're working out a proof on your own. Okay, let's consider a specific conditional, like this one. S and T, arrow S or T. What could you provide in a proof that would allow you to write this down? It says, if S and T were true, then S and T would be true. To put it differently, what should the conditional introduction rule look like? What could we assume or prove that would allow you to show that this conditional was true? You might think about it this way. Let's assume S and T is true. We write it down in a proof. And the idea is that if we assume S and T, then we can prove S or T. Here's how that might go. As a first step, we use conjunction elimination on line 1 to write down one of the conjuncts. So we write down S with the justification and E applied to line 1. Next, we can write down S or T using the or introduction rule applied to line 2. So the fact that we can give this proof, if we assume S and T, then we can show S or T, that shows if S and T, then S or T. The problem is that what we're missing at the bottom is a way to work this conclusion into the proof itself. What we have is just kind of a floating suggestion. So we've shown if we assumed S and T, we can get S or T. It's just something written down there below line 3. We need it to be part of the proof. In order to make it part of the proof, we put the conclusion as line 4. And if it's line 4, then a vertical line starting back on line 1 needs to continue through. That is, it needs to be part of the same main proof. Now, our 3-line proof, assuming S and T, showing S or T, ended after line 3. So we do this by having separate lines. The left-hand vertical line is the main proof. The main proof is ultimately where the action is. The conclusion has to appear as a line in the main proof. That other vertical line, the one that starts on line 1 and ends on line 3, is a subproof. The rule that justifies writing down the conditional on line 4 is conditional introduction. We abbreviate it arrow I. And the rule applies to the entire subproof, lines 1 through 3. Some of the rules we had earlier used a comma to indicate that they were referring to 2 different lines. The dash here is importantly different. It's not referring back to line 1 and also to line 3, but it's referring back to the whole subproof, 1 through 3, and we write that 1-3. So it's just a small difference in the punctuation, but it's importantly different conceptually. What is it doing? It's referring to that entire span of lines, that whole subproof. Here's how the rule looks on the reference sheet. You start a subproof, you assume A. The last line of that subproof is B. You can conclude, back out in the main proof, A arrow B by arrow introduction. So arrow introduction is a rule that requires a subproof, where you assume the antecedent and end with the consequent. Suppose we have this problem. given m or n and n or o, we want to prove not n arrow m and o. We start the proof in this way. We write down our two premises on line 1 and 2, and we write a horizontal line underneath that. Now, we want to end up with not n arrow m and o. Our premises don't give us much to work with. M or n, we might think to use or elimination, but or elimination requires two things. It requires the disjunction, m or n. It would also require the negation of one of the two disjuncts. We don't have that. Similarly, line 2 is a disjunction, and disjunction elimination requires two things. So we can't really do anything with lines 1 or 2 yet. So suppose we think about where we need to end up. If we need to end with not n arrow m and o, we could think about introducing that using arrow introduction. In order to apply arrow introduction at the end, if that's our plan, we need to start a subproof. We assume the antecedent, the left-hand side of the conditional that we want to prove. So we assume not n on line 3. And in this subproof, we want m and o. Notice that making this assumption gives us more to work with. Now we have not n available to us on line 3. And that means we can apply or elimination on line 1 and line 3 to get m. Because we have more than just the disjunction now, we also have the negation of one of the disjuncts. Similarly, since n is one of the disjuncts on line 2, and we have not n, we can get o by or elimination 2 and 3. We can now put those together to get m and o by and introduction on line 4 and 5. So that's what we wanted in the subproof. We wanted to get m and o. We've got it. So outside of the subproof, back in the main proof, we conclude not n arrow m and o by arrow introduction, subproof lines 3 through 6. The upshot of this is that when you're planning to apply arrow introduction, you need to start a subproof. You assume the antecedent, the thing on the left-hand side of the arrow, and you end the subproof when you get to the consequent, the thing on the right-hand side. But what allows you to start a subproof in the first place? If you think about it, the subproof doesn't actually show anything, really. On line 4, you're only allowed to conclude m because you have this extra assumption that you made on line 3. And that's just something you made up. We just made up not n and wrote it on line 3. There's not a rule that shows us that not n has to be true or anything. So you can think of the subproof as a game of what if. On line 3 we said, what if not n were true? What would follow from that? And lines 4, 5, and 6 are playing out the consequences of that game of what if. So things that happen inside the subproof aren't proven to follow from the premises alone. They're proven to follow if we're willing to add this extra assumption. We're playing the game, what if not n were true? Well, o would follow, and m would follow, m and o would follow. We're imagining not n, and we see what the consequences of that are. That ends after line 6, because the vertical line for that subproof ends. Back out on line 7, we're not inside the game of what if anymore. Formally, you can start a subproof at any time. You're allowed to make any assumption. That's because each subproof is just the exercise of imagining what follows from the assumption. You're saying, let's pretend for a moment that this is true and see what follows from that. The subproof goes on as long as the vertical line starts it. In this example, the subproof starts or opens on line 3 and ends or closes on line 6. Once a subproof is closed, you can't refer back to specific lines in it. Suppose in the earlier proof we'd tried to do this. That is, after the subproof was over on line 4, tried to use and introduction on lines 2 and 3. The and introduction rule calls for 2 lines, and that's why we write it with a comma. It's 2, 3. But the sentences on lines 2 and 3 only followed from the assumption that S and T was true. Once we closed the subproof, we dropped that assumption. So we couldn't help ourselves to whatever conclusions depended on it. We could, on line 4, apply arrow introduction, because the arrow introduction rule calls for an entire subproof. That's why we write it with a dash, 1-3, 1 through 3, referring to that whole subproof rather than to just specific lines inside it. The biconditional introduction rule will work similarly. For the biconditional, we need to prove both directions, so there need to be 2 subproofs. Suppose we have this problem. Given P arrow G and G arrow P, we can prove P biconditional G. So this is the setup. On line 1, we get the premise. And at the end, we need P biconditional G. The obvious plan is to use biconditional introduction. In order to do that, we'll need 2 subproofs. And in those subproofs, in one of them, we assume the left-hand side and prove the right-hand side. So assume P, show G. In the other subproof, we work in the other direction. Assume the right hand, show the left hand. So assume G, show P. That's the plan. So with that plan in mind, we start the proof. We've got our premise on line 1. We start a subproof on line 2, assuming P. We can get P arrow G from line 1 by and elimination. And that lets us get G. We can use arrow elimination on lines 3 and 2. That's what we wanted to have happen in the first subproof, so we can close it and start another one. In the second subproof, we assume G, and we want to end up with P. We can get G arrow P from line 1 by and elimination, and P by arrow elimination on 6 and 5. So we're done with that subproof. Back out in the main proof, we get P biconditional G by the double-headed arrow introduction rule, where our justification is the subproof on 2 through 4, comma, subproof on 5 through 7. So 2-4, comma, 5-7. You should start a subproof when you're planning on applying a rule that requires a subproof. If you aren't planning on doing that, don't start a subproof. At this point, the rules you have that require subproofs are arrow introduction and double-headed arrow introduction. Start a subproof if you plan to apply one of those rules. But don't start a subproof if you don't have one of those rules in mind.